Hi Stats Scholars. This week we're starting our lessons with some basics about hypothesis testing. A reminder that we're still in our unit on inference. So we're taking data from a sample and making statements about a population with it. For hypothesis tests, we use them to determine if a claim about a population parameter, such as a population mean or a population percentage, is supported by actual sample data pulled from that population. These tests are also known as significance tests, and they are performed for claims about a single mean, a difference in means, a single proportion, or a difference in proportions. There are several other significance tests, and we're going to see some more in week 6 and week 7, but for this week, we're going to focus exclusively on means and proportions. We're going to be using that same 4-step solution method that we used with confidence intervals for hypothesis tests. So we're going to be sticking with the state, plan, do, conclude method for the rest of the time in the course. So let's go ahead and take a look at what that looks like for a hypothesis test. For the state step, it's going to look exactly like it did for confidence intervals. In the state step, all we're doing is identifying things that were given in the problem. So you're defining the parameter of interest in words. Mu equals the population mean height of all students at Shasta College. And then you're labeling all of the given quantities and key phrases that were given in the problem statement. So we know in order to do calculations for means, we typically need to know a standard deviation, either a population value or a sample value. We need to know our sample size because we're basing this inference on a sampling distribution. So all of those things should be picked out of the problem and labeled. For the plan step, again, very similar to what it was for confidence intervals. We're going to identify the thing that we're doing. So is this a z-test for a mean? Is this a t-test for a mean? We would write that at the top. And then we're going to identify the hypotheses for our hypothesis test. And then last, we're going to calculate any related quantities that we need for our next step. And you'll notice here we have an example of two hypotheses. Our null hypothesis, HO, says that the population mean is equal to 5 minutes. And the alternative hypothesis, HA, says the mean is less than 5 minutes. And this is just an example, but that null hypothesis, HO, should always be a statement of equality. Your book will sometimes show you a less than or equal to or greater than or equal to. There always has to be an equal to in the null. The alternative is always a statement of inequality, less than, greater than, or different than, not equal to. And it's the alternative that we're testing. So the alternative, less than, greater than, or not equal to, is going to determine the type of test that we do. So by default, you're going to see most statisticians always make the null equal, and then the alternative will be dictated by what the problem says. Are we looking for a difference? Are we worried that the quantity is less than or greater than? Once we'd identified the type of test that we're doing, and we know that inequality for the alternative, we do some calculations. This is where the math comes in. So for significance tests, you're going to write down the appropriate equation for the test statistic. You're going to substitute values from the problem into that equation. And then you're going to grab your calculator and let your calculator find the value for that test statistic and the p-value, which is a probability. So you should never be having to evaluate that equation, but writing it out and substituting in the formulas constitutes showing justification for your answer. The test statistic is the z-score for our sample data in the sampling distribution. It tells us where our sample sits. And the p-value is the probability that a randomly selected sample is as extreme or more extreme than our sample. So it's telling us how likely it is that a randomly selected sample would be even further out in the tail than our sample is. In addition to these calculations, you should draw the appropriate distribution and mark where that test statistic sits and shade the appropriate tails in. And that's going to feel very similar to what we did for confidence intervals. If you used the Z for your test, you should draw a standard normal distribution. If it was a student t-test, you should draw the t-curve. The do step will look slightly different for each test because each test has its own test statistic. And we will go over those in the specific videos for each test we're going to do this week. Along with those new formulas for test statistics, there's also new calculator functions for each test. And the nice thing is those calculator functions are labeled exactly as we write them down on the page. So they're pretty easy to find once you know the names of the tests. Our last step, our conclude, is going to work exactly like it did for confidence intervals. You're going to have some sentence frames. That should say hypothesis tests instead of confidence intervals, sorry. And then you're going to complete those sentence frames using your calculations and words from the problem. The only difference from last week is hypothesis testing gets 2 sentence frames. One that addresses the null hypothesis and the decision we make, the other that addresses the claim, typically the alternative hypothesis. So the very first sentence frame says because the p-value of blank is less than or greater than the significance level of blank, we reject or fail to reject the null hypothesis. So you notice it's in terms of the null. So you're going to pull your p-value from your calculator, you're going to pull the significance level from the word problem, and then you're going to tell me whether the p-value is less than or greater than. If the p-value is less than, we reject. If it's greater than, we fail to reject. Then we summarize in terms of support for the claim. We're going to look more carefully at those as we go into individual tests, but really quick, how we make decisions in that last sentence. If the p-value is greater than the significance level, we fail to reject the null. So p-val is greater than alpha, fail to reject. If it's less than or equal to, we reject. And the reason we're doing that is remember that p-value is the probability that a randomly selected sample is more extreme than ours. So if that p-value is small, that's telling me that my sample's way out in the tail of that sampling distribution, and it's a very unlikely occurrence. I would not expect to see a sample like that from the population that I'm assuming to be true. And that is why when our p-value is small, we reject. If we fail to reject, that means we're supporting the null and not supporting the alternative. If we fail to reject, the null still could be true. If we reject the null, we do not support the null. We're saying it's not likely to be true, and we are supporting the alternative. We're going to come back to that, but that idea right there is how we write our second sentence in our conclusion. Sorry for the barky dogs. Next time, we're going to talk about type 1 and type 2 errors. Because we know that we're using sampling distribution and probability, we can be wrong when we do this process. And after that, we'll start looking at the very specific tests and do some examples that show you how those processes work for each test. As usual, if you have any questions, you can catch me in office hours on Tuesday and Thursday or via email. Otherwise, I'll see you in the next video.